We now present a heuristic argument that will lead to the formula for the capacity of the bandlimited wide Gaussian channel. We will not give a rigorous proof of this formula here, because such a proof would involve advanced tools in signal analysis which are beyond the scope of this course. Assume that the input process x'(t) has a Fourier transform so that x'(t) can be expressed as summation I from minus infinity to infinity xi prime times psi I of t. Note that there is a one-to-one correspondence between the continuous time process x'(t) and the discrete time process xi prime. Likewise, assume that the output process y of t can be written as summation I from minus infinity to infinity yi times psi I of t. With these assumptions, the waveform channel can be regarded as a discrete time channel defined at the sampling points t equals I over 2w, with the ith input and output of the channel being xi prime and yi respectively. To complete the model of the discrete time channel, we need to understand the effect of the noise process z' of t on the output process y of t at the sampling points, and relate the power constraint on the discrete time process xi prime to the power constraint on the continuous time input x' of t. One main idea of the heuristic argument is about sampling the noise process z' of t. Proposition 11.31 says that z' of I over 2w for I from minus infinity to infinity, that is, the value of z' of t at all the sampling points, are IID Gaussian random variables with zero mean and variance n0 times w. Here is the proof of the proposition. First of all, z' of t is a filtered version of z of t, and so it is also a zero-mean Gaussian process. Then z' of I over 2w for all I, which are samples of the process z' of t, are zero-mean Gaussian random variables. The power spectral density of z' of t is a rectangular function. Specifically, Sz' of f is equal to n0 over 2 for f from minus w to w, and is equal to 0 otherwise. This can be written as n0 divided by 2 times rect of f over 2w. The autocorrelation function of z' of t is a sinc function. It is because the power spectral density is a rectangular function, and the autocorrelation function is the inverse Fourier transform of the power spectral density. Specifically, the autocorrelation function Rz' of tau is equal to n0 times w times sinc of 2w times tau. Note that the autocorrelation function Rz' of tau vanishes at tau equals I over 2w for every non-zero integer I, because for such values of tau, 2w times tau is equal to a non-zero integer. More specifically, Rz' of I over 2w is equal to n0 times w for I equals 0, and is equal to 0 for I not equal to 0. Then for all t and for all I not equal to 0, z' of t and z' of t plus I over 2w are uncorrelated. It is because the expectation of z' of t plus I over 2w times z' of t is equal to the autocorrelation function evaluated at I over 2w, which is equal to 0. This implies that the covariance of these two random variables is equal to 0 because they have zero mean. Specifically, if any two random variables x and y are zero mean, then the covariance of x and y which is equal to the expectation of x times y minus the expectation of x times the expectation of y, which are both equal to 0, is simply equal to the expectation of x times y. Now, z prime of t and z prime of t plus I over 2w are uncorrelated. In particular, letting t equals j over 2w, we see that z prime of j over 2w and z prime of j over 2w plus I over 2w, that is z prime of j plus I over 2w, are uncorrelated. Here, j is an arbitrary integer, and I is any non-zero integer. This implies that the values of the process z prime of t at any two sampling points are uncorrelated. Therefore, the values of z prime of t at all the sampling points are uncorrelated and hence are mutually independent because these random variables are jointly Gaussian. Since the value of the process z prime of t at the sampling point I over 2w has zero mean, its variance is given by the autocorrelation function evaluated at tau equals 0. Because our z prime of 0 is equal to the expectation of z prime of I over 2w plus 0 times z prime of I over 2w, which is equal to the second moment of the random variable, and it is equal to the variance of the random variable because the random variable has zero mean. From step 5, we have that our z prime of 0 is equal to n0 times w, and so we see that the variance of z prime of I over 2w is equal to n0 times w. In summary, we have shown that z prime of t at all the sampling points are zero-mean Gaussian random variables. These random variables are independent, and each has variance equal to n0 times w. This completes the proof of the proposition. Recall that y of t is equal to summation I yi times psi I of t, and x prime t is equal to summation I xi prime times psi I of t. In the same fashion, we let z prime of t be summation I zi prime times psi I of t, where zi prime is equal to 1 over square root of 2w times z prime of I over 2w. Then y of t equals x prime of t plus z prime of t implies that for all I, yi is equal to xi prime plus zi prime. Because psi I of t, I from minus infinity to infinity, are orthonormal. Since c prime of I over 2w, the samples of the noise process are IID, where each one of them is a Gaussian random variable with mean 0 and variance n0 times w. The random variables zi prime are IID Gaussian random variables with mean 0 and variance n0 over 2. So, the band-limited white Gaussian channel, which is a continuous time channel, is equivalent to a memoryless Gaussian channel with noise power equal to n0 over 2, which is a discrete time channel. Because yi is equal to xi prime plus zi prime, and zi prime are IID Gaussian random variables with mean 0 and variance n0 over 2. Now we need to relate the power constraints of the discrete time input process and the continuous time input process. Let P prime be the average energy, that is the second moment, of the xi primes. Since the sinc functions psi I of t, I from minus infinity to infinity, are orthonormal, each has unit energy and the energy adds up. Specifically, the energy of psi I of t plus psi j of t, which is given by the integral of the square of psi I of t plus psi j of t dt, is equal to the integral of psi I of t square plus psi j of t square plus 2 times psi I t times psi j t dt. This is equal to the integral of psi I of t square dt plus the integral of psi j of t square dt plus 2 times the integral of psi I of t times psi j of t dt. Because psi I of t and psi j of t are orthogonal, this integral is equal to 0, and we see that the energy of psi I of t plus psi j of t is equal to the energy of psi I of t plus the energy of psi j of t. Therefore, the continuous time input process x prime t accumulates energy from the samples at a rate equal to 2w times p prime. Because there are 2w samples per unit time, by considering 2w times p prime less than or equal to p, where p is the average power constraint on the input process x prime of t, we obtain p prime is less than or equal to p over 2w. Thus, p over 2w is the equivalence power constraint on the discrete time input process xi prime. To summarize, the continuous time channel is equivalent to the discrete time channel with input xi prime, noise variable ci prime, which is a Gaussian random variable with mean 0 and variance n0 over 2, and the output of the channel yi is equal to xi prime plus zi prime, and the input power constraint is equal to p over 2w. Then the capacity of the discrete time channel is equal to 1/2 times log of 1 plus p over 2w, the input power constraint, divided by n0 over 2, the noise power. This is equal to 1/2 times log of 1 plus p over n0 times w in bits per sample. Since there are 2w samples per unit time, the capacity of the band-limited white Gaussian channel is equal to w times log of 1 plus p over n0 times w in bits per unit time.